Humans are capable of performing visual feedback tasks in a wide variety of environments, even novel ones they have never been in before. In contrast, robots, when doing similar insertion tasks in manufacturing, rely on special end effector tooling and precise data information, as the robot shown here attaching a BNC connector. If they need to be deployed in diverse scenarios and eventually open-ended environments like homes, they will need to be able to master visual feedback skills on the fly. We will study mastering visual feedback tasks on the fly in the industrial insertion domain shown here. How can we get robots to also acquire these visual feedback policies in novel environments on the job? More generally, how can we utilize offline data, shown on the left, for fine-tuning on an unseen domain with minimal human supervision, shown on the right? One possibility is offline RL on a diverse dataset, but offline RL initially performs poorly on unseen connectors, such as the one above. Since this connector is not included in the offline data, the zero-shot performance from vision is poor. So we need to fine-tune on the job to get better at such a task. In order to fine-tune, we first train a reward model on the offline data, as well as the policy and value function with implicit Q-learning, IQL, all from raw images. We introduce a novel representation learning objective, the domain adversarial information bottleneck, or DABE, to improve a generalization of the reward function and policy to new domains. We then fine-tune the policy in the target test domain, relying on the generalization of the policy and predicted rewards in order to improve. The representation learning objective, DABE, improves generalization of the reward function trained via classification. The results in this table shows a significant boost in the accuracy of the trained classifier on held-out connectors. Using this reward, we can fine-tune policies on unseen test connectors. The policy improves via offline to online RL, using its past data as well as newly collected data to improve. Here we're showing the training trajectories. We can see over time that the accuracy is improving over the course of the training scenario. We present results across 4 connectors and 2 scenarios. Our method successfully fine-tunes offline to online, significantly improving performance. Successful trajectories are paused and highlighted in dark. We compare against 2 sets of baselines. First, RL baselines, where we show the evaluations after an equal amount of fine-tuning time as our method. And second, standard robotics insertion baselines using localization and search. Across the range of 4 connectors and 2 scenarios, our method performs best compared against both RL baselines and traditional robotics baselines.